Hello, my name is Rand Migrod, and I will be talking about work with Tim Vieira and Ryan Cotterill about taking derivatives over distributions in weighted finite-state machines. Weighted finite-state machines, or WFSMs, have been used throughout NLP. Some examples of tasks where they have been utilized are morphology, phonology, speech recognition, and transliteration. We consider the study of their derivatives as they have been shown to be useful in finding expectations. In particular, we examine the Hessian of a WFSM, which can be used to find second-order quantities, such as the covariance matrix or the gradient of entropy. Formally, a WFSM is comprised of n states and accepts a string from an alphabet where each symbol leads to a transition. Each transition has an associated weight, and so we can represent the transitions as a weighted matrix. We really have such a weighted matrix for each input in the alphabet, but we can sum these together to create a single n by n matrix. We can do this without loss of generality, as we are considering sums over paths. We also have a start and an end vector, which gives the weight of starting or ending in a particular state. If we cannot start or end at a state, then its value will be 0 in the start or end vector. We are interested in the distributions over trajectories, or also known as paths. These are sequences of transitions that start at some state with non-zero start weight and end at a state with non-zero end weight. The weight of a trajectory is then the product of its transition weights. Given the weight of a trajectory, we can define the probability of a trajectory by dividing it by a normalization constant z. The normalization constant requires an exponentially large sum when done naively. Fortunately, we can use the Finite-star closure on matrices to find z. For the real numbers, this is equivalent to taking a matrix inverse, and so can be done in cubic time. So why do we need the normalization constant? If we wish to train a model using a negative log likelihood loss function, or we wish to have a loss function based on an expectation such as risk or entropy, we need to be able to find z and its derivatives. As I mentioned, we can find z using the Finite-star algorithm. A simple Python implementation of this algorithm is given on the right. There exists two methods using automatic differentiation techniques to find its derivatives. We will look at these two techniques for finding the Hessian. The first method is using forward mode automatic differentiation. In this method, each element of our matrix is a nested dual number, and so is the size of the Hessian, which is n to the 4 in our case. Each operation of the algorithm must be adapted to this n to the 4 element, and so each operation costs big O of n to the 4 time. Since we have n to the 3 operations, we have a total runtime of n to the 7, which is far too slow for any reasonably sized WFSM. The second method is to use backwards mode, also known as reverse mode automatic differentiation. Reverse mode AD allows us to compute the derivative of a function that outputs a scalar in the same time as it takes to execute the function itself. Therefore, we can get the first order Jacobian in cubic time as we can find z in cubic time. In order to get the Hessian, we need to differentiate each element of the Jacobian. As there are n squared elements in the Jacobian, finding the Hessian takes n to the 5th time. This is already much better than using forward mode AD, but we can still do better. So far, the two methods using automatic differentiation lead to suboptimal algorithms. The Hessian is of size n to the 4, and so the optimal runtime to materialize the Hessian should also be n to the 4. It is possible to achieve this optimal runtime by exploiting repeated work when finding the derivatives. To see this pattern, we exploit identities from the matrix cookbook. We can find z using a matrix inverse and vector matrix products. If we let S and E be the following vector matrix products, we can write the first derivative of z using a scalar product of S and E. Taking the derivative again, the second derivative can be written as a sum of two scalar products. Now importantly, we only need to compute W star S and E one time, and then we can reuse the work to find each element of the Hessian. Therefore, we can find each element of the Hessian in constant time, meaning we achieve the optimal complexity for materializing the Hessian. I will next briefly discuss extending this approach to higher order derivatives and the use of the Hessian in finding second order expectations. One application of finding the Hessian is for second order expectations. Briefly, a second order function of a trajectory is one which is the outer product of two functions which decompose additively along the transitions. Some examples of this are the covariance matrix or the gradient of entropy or risk. More detail regarding second order expectations can be found in Leon Eisner or in our recent tackle paper, which you can access through this QR code. Finding a second order expectation can be directly done using the Hessian due to the connection between gradients and expectations. We show that it is possible to achieve a potentially faster runtime than n to the 4 by exploiting the distributive properties of some of the equations in order to get the second order expectations. Finally, our method for finding the Hessian can be applied to higher order derivatives of z. As we take more derivatives, we find a pattern that says that the nth derivative of z is a sum of products of the elements of w star, s, and e. We therefore need to do n cubed work to find w star, s, and e, and then we just need to sum over the products, which is done in m times m factorial time. Since we have to do this sum for each element of the mth derivative tensor, we have to repeat this work n to the 2m times. Thank you very much for listening. Our paper can be found using this QR code, and our code is publicly available on GitHub.